In this lesson, we will try to find an antiderivative for the integral of e to the x squared with respect to x. We will first try the usual methods, substitution and integration by parts, and see why they fail. Then, we will introduce a new approach using an infinite power series. First, let us try substitution. Let u equal x squared. Then du equals 2x dx, which means dx equals du divided by 2x. When we substitute, the integral becomes the integral of e to the u times 1 over 2x du. But we still have an x in the denominator, and x is square root of u, so the integral becomes the integral of e to the u over 2 times square root of u du. That did not make the integral any easier. Next, let us attempt integration by parts. Let u equal e to the x squared and dv equal dx. Then du equals 2x times e to the x squared dx, and v equals x. The integral of e to the x squared dx equals x times e to the x squared minus the integral of 2x squared times e to the x squared dx. This new integral is actually more complicated than what we started with. So, the usual methods do not work. This integral is non-elementary, which means it cannot be expressed using polynomials, sines, cosines, logarithms, or similar basic functions. Instead, we will use a power series approach to represent the antiderivative. Recall the Taylor series for e to the t. E to the t equals the sum from n equals 0 to infinity of t to the n over n factorial. If we let t equal x squared, then e to the x squared equals the sum from n equals 0 to infinity of x to the power 2 n over n factorial. Let us also write the first few terms. Because the series converges for all real x, we can integrate term by term. The integral of e to the x squared dx equals the integral of the series of x to the 2n over n factorial dx, which is the sum from n equals 0 to infinity of x to the power 2n plus 1 over 2n plus 1 times 1 over n factorial plus c. Let us write several terms explicitly to see the pattern. You may also see this antiderivative written using a special function called the imaginary error function. Specifically, the integral of e to the x squared dx equals square root of pi over 2 times phi of x plus c. The series we derived is exactly its Maclaurin series. To build intuition, let us compare e to the x squared with its partial sums near 0. The blue curve is e to the x squared. The orange curve is the first partial sum, 1 plus x squared. The green curve adds x to the 4th over 2 factorial. The red curve adds x to the 6th over 3 factorial. Notice how each added term improves the match near x equals 0. To summarize, the integral of e to the x squared does not have an elementary antiderivative, but using the power series, we obtained a clean formula that works for all real x.